is brown, it stinks, and it could be coming to ruin your next beach vacation.
About 38 million metric tons of the Sargassum seaweed, a brown, prickly algae, has been smothering Caribbean shorelines over the last month.
In the summer of 2018, the Caribbean Sea coughed up a brown tide so vast it could be seen from space.
It started in 2011. Millions of tons of the free-floating brown seaweed called Sargassum, stretching for thousands of kilometers in the Atlantic Ocean, enters the Caribbean.
It smothered beaches, emptied hotels, and choked entire towns into silence. But beneath the stench and chaos, a question surfaced. What if this wasn't a crisis to clean up, but a raw material waiting to be understood? When the ocean turned against the shore, it began not with a storm, but a slow, suffocating tide. Along Mexico's Caribbean coast, beaches once hailed as postcard perfect vanished beneath meters of rotting seaweed. In places like Playa del Carmen and Tulum, locals woke to the same scene each morning, shorelines buried under dense mats of brown algae, stretching as far as the eye could see. Tourists, drawn by turquoise waters and white sand, fled in droves. Fishing boats remained anchored, unable to cut through the viscous swells. The air turned acrid with the smell of hydrogen sulfide and decay, so potent that entire beach towns were forced to evacuate. The invader had a name: Sargassum, a floating seaweed that had for centuries drifted harmlessly in the open Atlantic, playing host to crabs, eels, and young turtles. But this was different. Sargassum had arrived in quantities no one had seen before. Over 20 million tons of it surged into Caribbean coastlines in 2018 alone, blanketing ecosystems, clogging tourism economies, and igniting panic. The response was swift but short-sighted. Millions spent hauling it to landfills, shoveling it by hand, and building floating barriers to hold it at bay. To most, it was an unsightly, toxic waste-choking paradise. Yet, a small group of engineers and one unassuming brickmaker saw something else. They didn't ask how to get rid of it. They asked why it had come, and what it might become if treated not as a pollutant, but as potential. The bloom that shouldn't exist. For centuries, Sargassum belonged to a stable ecosystem in the North Atlantic, known as the Sargasso Sea, a 2 million square mile gyre where ocean currents spiral gently, holding vast mats of the seaweed in quiet suspension. In this floating nursery, marine life thrived undisturbed. Sargassum was part of the ocean's architecture, a vital but contained presence. Then, in 2011, something shifted. And over the next 7 years, that shift became a rupture. By 2018, satellite data from the University of South Florida showed that the annual bloom had grown from about 1 million tons to more than 20 million. The Sargassum was no longer just drifting, it was migrating. Currents pushed it south into warm Caribbean waters, far from its historic home. It clustered around tourist coasts, smothered coral reefs, and reshaped entire marine food webs. The question wasn't just how, it was why. The leading theory centered on a chain reaction that began thousands of miles away. In the Amazon basin, rapid deforestation had loosened nitrogen-rich soils, which poured into the Atlantic via the Amazon River. Combined with agricultural runoff and warmer ocean temperatures, this influx created the perfect conditions for Sargassum to thrive. It wasn't just blooming, it was being fed, fertilized, and carried on altered currents into unfamiliar shores. What emerged was the largest macroalgae bloom ever recorded, a floating belt of biomass stretching from West Africa to the Gulf of Mexico. Scientists dubbed it the Great Atlantic Sargassum Belt. It could be seen from space. It was impossible to ignore. Yet, even as governments scrambled to mitigate the damage, the full ecological meaning of the bloom remained elusive. Was this a freak occurrence or a new normal? No one could say for certain, but one thing was clear. Sargassum wasn't going away. Waste or wonder. While government agencies struggled to keep beaches clear, a brickmaker named Omar Vasquez Sanchez took a different approach. In his garage in Quintana Roo, far from any laboratory, he began to tinker with the piles of Sargassum piling up at his doorstep. He wasn't a materials scientist, but he understood earth and clay, how to shape it, dry it, and build with it. His early attempts to mix Sargassum into bricks failed spectacularly. The prototypes cracked. They stank. They attracted insects. But he kept experimenting, shifting ratios, adjusting textures, learning from failure. Then, something unexpected happened. At a ratio of 20% Sargassum, 40% clay, and 40% sand, the bricks didn't just hold together, they outperformed standard concrete blocks. Compression tests showed they could withstand 60 kilograms per square centimeter, surpassing Mexico's minimum building code by a wide margin. The reason lay in Sargassum's structure. Its cellulose-rich fibers, when compressed and dried, acted like microscopic rebar, interlocking with clay and creating a stronger, more cohesive matrix. Meanwhile, lignin, an organic polymer within the algae, acted as a natural binder, reducing the need for cement entirely. But the breakthrough didn't stop with strength. The bricks were thermally efficient, with a conductivity of just 0.45 watts per meter Kelvin. Standard concrete blocks conduct heat nearly 4 times faster. In the sweltering heat of Quintana Roo, this meant cooler interiors, lower air conditioning costs, and a passive form of climate control built directly into the walls. Vasquez hadn't just found a way to reuse waste. He had engineered an affordable, sustainable alternative to one of the most carbon-intensive materials on Earth. And he had done it not in a lab, but on the edge of a crisis, driven by necessity, persistence, and a refusal to see trash where others did. Solving the chemistry. A strong brick is only as reliable as its chemistry allows. Early batches of Sargassum bricks, though structurally sound, revealed a new problem over time. Embedded within the algae's fibrous body was salt, more than enough to raise red flags. Even after rinsing, residual sodium chloride clung to the organic material. In the humid climate of Quintana Roo, that salt slowly migrated to the surface, forming a white crystalline film known as efflorescence. Worse still, in the presence of moisture, it could corrode steel reinforcement inside walls, threatening structural integrity over time. Rather than abandon the project, Vasquez and his team went back to the lab. They implemented a 2-stage washing process, first with fresh water to eliminate surface salts, then with a diluted vinegar solution to break down chlorides chemically bonded to the algae's tissues. After drying, the salt content fell below 0.5%, a safe threshold by engineering standards. But Sargassum carried another risk. Depending on where it drifted from, some blooms were laced with heavy metals like arsenic and cadmium, absorbed from deep ocean upwellings. To address this, the team instituted mandatory batch testing. Every ton of raw material was screened, and any contaminated loads were diverted to other uses like biogas production. Meanwhile, the bricks avoided the carbon footprint of traditional materials by relying on a centuries-old technique, sun drying. After 28 days beneath mesh tarps, with no kilns or fossil fuels, the bricks achieved full strength. Clean, efficient, and certified, these bricks were no longer just a curiosity. They were ready for walls, beyond the brick. By 2024, over 2 million Sargassum bricks had been laid into homes, schools, and community centers across southeastern Mexico. Yet, the story didn't end with construction. As word spread beyond Quintana Roo, researchers across the globe began experimenting with the algae's potential, not just as an alternative, but as a foundation for a new class of sustainable materials. At the University of Nottingham, scientists pushed the idea even further. They developed a groundbreaking biocomposite by merging Sargassum with mycelium, the root-like structure of fungi, known for its ability to grow into dense, fibrous networks. The result was a lightweight, fire-retardant material with outstanding sound insulation and a natural resistance to mold. Unlike concrete, which persists for centuries as waste, this composite degrades safely at the end of its life cycle. It was durable, certifiable under EU standards, and biodegradable, and it was built entirely from what the ocean didn't want. The discovery marked a turning point. Sargassum was no longer just a regional response to a local problem. It had become a global design material, one that could underpin the architecture of a circular economy. In this light, the once unwelcome algae was being transformed into an agent of regeneration. By fusing marine biology with fungal engineering, researchers had unlocked not just a cleaner material, but a new way of thinking. What began as an environmental nuisance had become a platform for innovation and possibly a path toward construction that leaves no scar behind. The race for Sargassum. Just as the world began to understand Sargassum's potential, the ocean offered more. NOAA projected that 2024 would bring the largest bloom on record, over 24 million tons stretching from West Africa to the Gulf of Mexico. This wasn't just a crisis anymore, it was a resource influx of planetary proportions. Suddenly, interest surged beyond coastal communities. Governments launched pilot projects in Yucatan and Campeche. Startups emerged, promising new processing technologies. But while the enthusiasm grew, so did the urgency. Processing sargassum isn't instant. The bricks need to be collected, washed, dried, and shaped, each step requiring labor, infrastructure, and time. Without rapid scaling, the material's promise could drown under its own abundance. Analysts estimated that if nations coordinated effectively, they could process up to 8 million tons of sargassum annually, enough to build 400,000 homes per year. But the window was narrow. If industrial players moved in first, the race could shift from solving ecological imbalance to securing control of a valuable feedstock. In this emerging market, the question was no longer who could clean the beaches fastest. It was who could build the future, brick by brick, before the tide receded. They nearly buried it in landfills, millions of tons of seaweed no one wanted. But what if the ocean was sending us the scaffolding for a new kind of world? If sargassum could build homes, what else have we been throwing away? Drop your thoughts below. Subscribe for more stories that rewrite the rules of waste.